Okay, so we're about to branch into um, 3 dimensions and start sort of on the simplest possible tools that are available for um, viewing in 3 dimensions. Now, my personal preference would be to be in front of a group of people and doing some demonstrating on the board, but also I would utilize this tool thanks to the wonderful people at GeoGebra for making this available for students and teachers. So this says 3D, and this is definitely not in 3 dimensions, but I want you to see sort of how we view the third dimension. In 2 dimensions, these 4 regions are called quadrants. This is quadrant 1. So I want you to imagine that this piece of paper is now rotated on your desk, but you're standing up next to your desk looking at it. And we'll do a little rotation here. So this would be the third dimension, but there's your quadrant 1. So this is the x-axis right here, and this is the y-axis. This is the z-axis. This will be sort of our standard orientation for viewing things in 3 dimensions. Sometimes it will be drawn, you know what, this graph, since it's so good, I can't show you my hand version, which is not so good. But when we do some sketching of some 3-dimensional surfaces that are sort of key to the course, I'll do a lot more demonstrating by hand. This is more, what are some simple tools and how does it look without needing special fancy 3D holographic glasses. So here we go. So the x-axis is here, and the y-axis is here, and the z-axis. Now, how many regions is all of space divided into? How many regions in total are we divided into? Ooh, I can get it spinning. There we go. Well, there are 4 regions above the ground, we'll call it, and there are 4 more regions below the ground. These are called octants. There are 8 of them, 8 octants. The only octant we're going to worry about the numbering of is the first octant, which is where x, y, and z are all positive. So it basically is over here. We will not worry about the numbering system for the other octants in this course. You might in other courses. So x, y, z are all positive there. This is the only octant we will specifically identify. So on my little review sheet, I have some questions, and if you're following along with it, you realize I just filled in several blanks. Pause, rewind, fill in the blanks. But if you're just listening and watching about 3 dimensions, let me just plot a point. If x coordinate is 2, and the y coordinate is 0, and the z coordinate is 0, there you go. There's the point. 2 units out on the x-axis, 3 units out, 4 units out, and you can see this is adjusting to it. That's kind of cool. If I were to go 1 unit in the y direction, look at its coordinates, 0, 1, 0 up here. If I were to go backwards, 1, 2, 3, 4 units there, the y value is -4, but the x value is 0 and the z value is 0. You'll hear me talk about I'll use the word the ground quite often. The ground is this gray plane where the x and the y-axis live. It's our paper, basically. 0, 0, 5 is a point that I have on my list of problems to look at, so let's just move this one up 5 units. Oh no, I don't think I've got it on the axis, do I? Well, let's type 0, 0, 5 here. There we go. There's a point vertically, 5 units above the ground, so to speak. Okay, so we're not going to do a lot of graphing of points, but we are going to look at coordinates that concept quite a bit more. So we need to understand, if, for example, this is a classroom and that's the front of the room, you'd be looking at the z-axis and the y-axis, and the x-axis is the one that's shooting straight out at you. That's a little bit different arrangement than normal. So there's z going up and there's y going to the right, but x is the one that's coming out at you if we had that ability to view in 3 dimensions. Now, moving ahead on my list of questions that we're going to look at, I want to go switch to another tool, and that tool is asking to measure the distance between 2 points. So the formula for distance is an extension of our distance formula in 2 dimensions. I have a proof or a derivation of this on a separate document available for my students. It's not too difficult to prove that it's very similar to what many of people call Pythagorean's theorem. The distance between the 2 x values squared, the distance between the 2 y values squared, and the distance between the 2 z values squared. Find the sum and take the square root. Not too difficult. I don't typically keep this memorized because of the following reason. Let's go to an example. The point 3, 4, and -2 to the point 0, 9, 0. Well, from 3 to 0 is a loss of 3 units. I don't need a formula to see that. Maybe I do want the formula though, then I'll use the formula. From 4 to 9 in the y direction is an increase of 5, and from -2 to 0 in the z direction is an increase of 2. Square them, find the sum, and you will find out the distance between those 2 points is square root of 38. A little bit more than 6 units. We'll use that distance calculation quite a bit more with something that comes up a little bit later. Now, it's a calculus course. We're not quite ready for the calculus aspect of this yet, but if we're learning some basic algebra in 3 dimensions, what else is there besides what we have right now? And so what we're going to do is we're going to look at something that's not too difficult, and that is the equation of a sphere. Sphere would be a lot like our circle in 2 dimensions. If we have a sphere with this particular center and this radius, I'm going to just give you the formula here, but you'll see that this formula is nearly identical to the distance formula, and that's not an accident. It's why I chose to go with the sphere first as opposed to something like the equation of a line. If you know how to plot 2 points, what's the distance between the 2 points, we can write the equation of our sphere. So x minus the x coordinate, y minus the y coordinate, z minus the z coordinate. Square them, find their sum. That equals the square of the radius. So if we wanted to do a simple example, the equation of the sphere centered at 3, 4, and -2 with a radius of 0, sorry, not a radius, we don't know the radius. It says the sphere has this point on it, 0, 9, 0. We would start with, well, I know the center, 3, 4, and -2. I'll substitute these values in our equation. And if this were intermediate algebra or pre-calculus, I would definitely slow down a bit more here. But we've done these kind of substitutions literally for years before we get to this point. But I don't know the radius. Well, it turns out the radius is the distance from the center to a point on the sphere. And if these coordinates look familiar to you, it's because we just found the distance between those 2 points. It was the square root of 38. So right here we'll find the equation of our sphere, x minus 3 quantity squared plus y minus 4 quantity squared plus z plus 2 quantity squared. That is equal to 38. Piece of cake. Now, in my list of problems, one of the other questions that's there is a direction that says, can you sketch a sphere? Can you sketch a sphere? I didn't use the word graph. Graphing requires a little bit more precision, and we don't have a three-dimensional graph paper. We're going to sketch it, and so I'm going to walk you through sort of Mr. Pipkin's little tricks here. To sketch the sphere, I start with a circle. That's supposed to be a really nice circle there. Then to the circle I add a belt, a little arc from here to here. If you'd like it to look more three-dimensional, you could add a little dotted line back here to represent the rest of the, what could we call this? The equator on our globe, maybe? And that would be a sphere. Either one of these would be a sphere. To put the sphere centered at the origin, we could add these axes and have the z-axis coming out and the x-axis coming out and the y-axis coming out. This particular sphere has a radius of 4 units. This is not a work of art. I'm not making profit selling these on the little art sale. What I am doing is sort of representing the physical world of the sphere. If we want to look at it in a nicer form, there would be the sphere of radius 4. You'll be able to see that it goes to the point 0, 4, 0, and also through the point 4, 0, 0, and also to the point 0, 0, 4, if we wanted to, those key points. And this looks nicer than mine by far, but if you're just trying to get a quick representation of it, a little sketch is more than enough. Let's look at one more sphere and then one more item on the graphing tool. So we're going to find the center and radius of the sphere that's given here. So we're going to use a process called completing the square. So we separate our terms with x, y, and z and move our constant term 10 to the other side of the equation because it is an equation. Then we add the term here that completes this trinomial squared, and we add the term here and we add the term here. And let me clear this up here so we can see, yes, half of negative 8 is negative 4. You square that is 16. Half of 2 is 1. You square that, you get 1. Half of 5 is 5 halves. You square it, you get 25 fourths. And we add to both sides, and we end up with the equation of our sphere. Maybe been off the camera here a little bit. So we have here x minus 4 squared, y plus 1 squared, and minus 5 half squared is 53 over 4. Center filled in. Radius, root 53 divided by, where'd the 2 come from? Oh yeah, the square root of 4 is 2. Okay, we're close. I'm just going to power through here. One more set of details in 3 dimensions. My little set of problems I'm offering my students is what's called simple planes. Now they're called simple planes but they may not be as easy to sketch as the sphere we were just looking at. So let me just type in a really short equation, x equals 3 into the graphing tool. And I want you to see here, we just got this blue wall just appeared. And I would like to show you what happens if you select a point, 3, 0, 0, that has the coordinate where x value is 3, 3, negative 5, 2. If you choose points where x equals 3, you will get points on this wall here that is 3 units away from the whiteboard, so to speak. Okay? The concept is not too difficult, but I struggle a little bit when I'm trying to sketch this myself. What if this were to become, let's just turn that one off. What if it were y equals 3? Well, now that's 3 units out in the y direction. Alright, I can sort of see that. I guess you could call it a vertical plane, but it depends on what your orientation is there. And what if it was z equals 4? Ooh, that one's 4 units over the ground. Well, what if it was z equals like negative 2? Ooh, that's 2 units below the ground. And y is negative 3. Let's turn it back on again. There we go. 3 units back. Those aren't too difficult to imagine. So my list of questions that I have for my students, I ask about what's called the XZ plane. The XZ plane. Well, the XZ plane is where we have the x-axis and the z-axis, and the y-axis meets it right there, and it happens to be the place where all the y values are 0. X, z-axis is on it, the y values are 0 there. And the YZ plane, you want to guess? Well, that's right, that's where all the x's are 0. That would be kind of like the front of the room or the board I'm drawing on, and the x-axis comes shooting out at me. And finally, the XY plane, our traditional piece of paper, that happens to be where all the z values are 0. Ooh, that's kind of interesting. So it happens when the planes intersect the ground. That's kind of trippy. All right. So there's a little introduction to some beginning three-dimensional concepts. So we'll do some vectors next.